Okay, let's review quickly what we did last time, and then we're going to go on from there. So a set is any collection of things. Here's a set, which is the alphabet. The cardinality of the set is just the number of things in the set. So the number of things in the alphabet are 26. We use this notation to say that something is in there. H is an element of U because it's in there. Alpha is not an element of that set. Then we have these things, which are called subsets. I guess I didn't write it here, but a subset is just any portion of your first set. In this case, there's your set. This is a subset of it. And so this is a subset. Everything in here is in U. Here's another subset. The complement of V is everything that's in U but is not in V. So you start with U and you get rid of everything that's in V, and whatever's left over are the consonants. So you could also write V prime is a subset of U because everything in here is in there as well. Two sets are equal if they have exactly the same elements. So for example, I'll just do it up here. The set A, B, C is equal to the set C, A, B because they have exactly the same elements. It doesn't matter what the order is, and so then you'd say that they are equal. A set is infinite if they have, if you don't have a finite, if you have an infinite number of elements in it. And then we talked about intersections of sets. The intersection of two sets is everything which is in both of them. The intersection of A and B are the elements E, F, and G. And we have some other ones as well. The union of two sets is everything which is in one or the other, or both. As long as it's in one or the other, then it's in the union. So you dump them together. And you think of this as basically the bowl that holds everything that's in either one. So it'd be A through G. And then we've already got those, so then you would also include H, I, and J, and it doesn't matter what the order is. The empty set is the set with nothing in it, which is denoted like this. We already talked about subsets, so these are all subsets, and so on. So very good. So now, given this Venn diagram, So I'll plug in my power. Okay, sorry about that. So now that we have a Venn diagram, let's see once where these various elements would be. So what's in V? V are all the vowels, A, E, I, O, and U. B is the set with E and I in it. So E would be right there. I would be right there because they are in both the set V and they're also in the set B. In fact, E is in both A and B and V, isn't it? E is in all three of those. So E would be right there because it's both in V and it's in B and it's in A. I would be right there. Here's the intersection of A and V. So A and V would have A in it. Right there. So A is in both of these, I is in both of those, and E is in all three of them. What are your other vowels? A, E, I, O, and U, and Y. Those are vowels, but they're not in either B or A. What are the things that are in B and A but aren't vowels? B and A are, let's see. B and A are these three things right here. We already have E included here, so F and G would be right there. So F and G would be right there. What else is in B? We've got I, E, F, and G. So H and J would be right there. What else is in A? What do we have already? We have A, E, F, and G. A, E, F, and G. So we still have B, C, and D. So B, C, and D are still in there. And then everything else, which is not in there, would be out here. So this would be what? We've got everything included up to J. So you'd have H, I, J. So K would be here, L, M, N. O is a vowel, we've already got that. P, Q, R, S, T, U is already there. V, W, X, Y is right there, and Z. See how that works? So that's how you can use a Venn diagram to basically show kind of the relationship between sets. Okay? So with all that, let's do just another example just to kind of make sure you're solid on this stuff. The ideas are simple, you just want to make sure they're solid. So before we go on to a couple new ideas, let's just reinforce the things we've learned with one more example. Let's let U, the universal set, be all the numbers from 1 to 20, all the counting numbers from 1 to 20. So there's your set, and then I'll let T, which stands for threes, be the set of all multiples of 3. 3, 6, 9, 12, 15, 18. And then I'll let F be all the multiples of 5. 5, 10, 15, I guess we have 20 yet, right? So there's 5s. And we'll let one more, we'll let S stand for the multiples of the 6s. 6, 9, 12, 18. Okay, so there's some sets. So what are some various things we can do with these sets? If I want to, I can say, for example, that 10 is an element of the set F, right? Or, just to stress the point, I could say the set with 10 in it is a subset of the set F. Or I could say the set with 10 and 15 in it is a subset of F. Or, of course, I could say that the empty set is a subset of F, just using F as an example. So we've got all those. What are some other things we can say? Notice that everything that is in S is also in T, right? So I could say that S is a subset of T. If I wanted to, I could go on and say that T is a subset of U, right? So those are all true statements. You can make up some other ones as well. So we've got all those. Then if we want to, we can take intersections of sets. What's the intersection of F and T, for example? F intersect T. That's everything that's both in here and in here. So it's got to be a multiple of 3 and a multiple of 5. I guess 15 is the only one, right? So that would be the set with just 15 in it. If we wanted to, we could say, what is the union of F and T? Okay, what's the union of F and T? So here's F, here's T. So it's going to be all the things in F, 5, 10, 15, 20. And then all the things in T, 3, 6, 9, 12. We already have 15, notice, so we don't put it again. 18. Okay, so there's F union T, the union of F and T. Okay, very good. Let's go ahead and make ourselves a Venn diagram just to capture all of this. So again, this will be our set U. U is the set of everything. And then here will be the set of 3's right there. And notice that the 6's are a subset of 3's. So the 6's would be, for example, all of these things. What would be in here? This would be, oops, I didn't mean to have 9 in there. My fault. 6, 12, and 18. Okay, so those are the multiples of 6. Okay, so this would be 6, 12, and 18 would be in here, and 3 should have the others. How about 5's? So notice that 5's, there would be the 5's right there, and notice that there's an intersection, right? These things intersect with the 3's. What did we say was in the middle of them? 15 is in the middle of them. So you've got 15 right there. And what else do we have? We have 3, which would be right there. 9 would be right there, for example. 3, 6, 9, 12, 15, 18. So there they all are. What are the multiples of 5? You've got 5, 10, 15 is in here, 20, and so on. So those are all those. And then what are the things that are in here? Those are the things that aren't in any of these sets. So 1, 2, 3, 4, 5 is in there already. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I guess those would be in there like that. So there's a Venn diagram. That's a good way of seeing again the relationship of sets. Here's one other thing I'll mention to you. What is the cardinality? Remember the notation for cardinality? It's the number of elements in a set. What is the what number of elements? How many elements? Let me just ask it like that. How many elements are in F union T? Well, if you think about it, you could take all these elements. How many are in T? 1, 2, 3, 4, 5. Sorry, 1, 2, 3, 4, 5, 6. There's going to be the number of elements in T. And then here's all the number of elements in F. So you would add those together. Is that going to be true? How many elements are in here? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. How many elements are in here? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Why do these add up to more than this? Why do these add up to more than this? Well, do you see the answer? It's because I included 15 both times. It was in this set and also in this set. So if you want a formula for this, it would be you take all the things in here, add it to all the things in here, but then since these things here were included twice, you have to subtract off the number of things in F intersect T. See that? So there's a nice little formula. And again, you don't memorize a formula like this, just understand it. Okay, it's if you were to count all the things in F, you'd go 1, 2, 3, 4, and then all the things in T as well, you'd go 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is that what we said? Did I? Oops. Oh, that's S. That's not a 5. That's an S there. Sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's an S. Make sure that looks like an S. Okay, yeah. So there's 9 of them, right? So you added all the things in both of those. You only want to add that once. Okay, very good. Just one other thing. Well, actually a couple other things. One other thing you can do with sets, and I'm going to get rid of this in order to do it. is you can take the cross product of two sets. So let's take the cross product of F and S, for example. So here's F. Notice that F has 4 elements and S has 3. So I'm going to take F cross S. Okay? And here's what I mean by doing that. What you do is you collect all the ordered pairs. Now remember what I said about a set. A set, you don't care what the order is of the things in the set. It could be whatever order you want. But an ordered pair, by the very use of the name, notice it has the name ordered to it. It also says pair, which means you're going to have 2 things in there. An ordered pair is a collection of things like this. So basically, it's a collection of things where the first, since this F comes before the S, you take the first coordinate of the ordered pair, and then you put a comma, and then you take the second coordinate of the ordered pair comes from S. So there is one thing in F cross S. Let's find another thing. Here's another thing. We could take 5, and then instead of the 6, we could take the 12. Or we could take the 5, and instead of the 12, we could take the 18. So we got 3 of them there. Notice how many more you can get. You can start with 10, and then 6, 10, 12, 10. The first one always comes from here, 18. So these are all ordered pairs. Can you see what the next ones are going to be? 15, 6, 15, 12, 15, 18. And then finally, 26, 20, 12, and 20, 18. See that? So that's the whole collection. That's the whole collection right there. That's another whole set. I'll put those aren't very good parentheses, are they? Let me make them a little bit better. I think drawing them this long in my life, I should make them better than that. Braces. I guess they're called braces rather than parentheses. So there they all are. So these things are all members of this set. And these things can be in any order that you want, because that's a set, so you can put them in any order you want. But each one of these things individually need to be, the first thing has to come from F and the second thing has to come from S. And now, what if I were to ask you this question? What are the number of things in F cross S? How many things are in there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Can you see the rule? Because you take each of these things and each of these things and pair them, so it's just going to be the number of things here times the number of things here. So this is just going to be the number of things in F times the number of things in S. See that? So there you go. Okay, very good. Just one more thing I want to show you about sets. Named after mathematician DeMorgan. Here's what DeMorgan discovered. He said if you have some sets, well, we'll just restrict it to 2 in this case, but if you take a collection of sets and you take the union of these 2 and then take the complement of that, you're going to end up with the complement of the first. That's a union, so now you go intersect the complement of the second. Okay? So I like to say it, the complement of the union is the intersection of the complements. That's one of DeMorgans laws. The other one is almost the mirror image. If you take this thing and go like that, can you see the words? The words kind of help you out. The complement of the intersection is the union of the complements. Okay, so this one is always the opposite of that one, and here you have them pulled together, and here you have them separate. So these are called DeMorgans Laws. And I mention them to you because they are important in their own right. They show up not only here, but in probability and various other places in mathematics. And they also allow us just to show how you can use a Venn diagram to kind of prove that they're true, to show that they're true. Okay, so let's let this set be A, and let's let this set be B, and let's see what each one of these is asking us to get then. So I'm going to use two different kinds of color here. Let's use blue and red. Let's first do this one in blue. What does this one say to do? It says to take the union of the two sets. Well, do you agree the union of the two sets is all this stuff right here? Once you have the union, by the way, this is U right here. This is your universal set. That's where they both live. So A union B is all this, and once you have A union B, then you take the complement of it. So the complement of it is everything that's not in A union B. So it's going to be all this stuff, out there. Okay, that's what the left-hand side. We put a blue line under there to indicate that's the left-hand side. Okay. Now, what about the right-hand side? The right-hand side says to do what? It says to first take everything that's not in A. Well, if it's not in A, then it's going to look like that. Can you see it? All this stuff is not in A. And now you take all the stuff that's not in B. Okay, if it's not in B, then it's going to look like this. I'll use a green marker here. Not in B. So it's not in B. Okay, there you go. So what does this say? So this thing here is red and green together. It's the intersection of red and green. In fact, let me do it like this. The first one was everything not in A, so this is the red one here. And then here's the green one, not in B. Okay? And this is the blue one. All that. Okay? So let's see if we agree. So the blue color, notice what the blue color is. That's all this stuff here along the outside of both circles. It says that is equal to the intersection of these two. So we want the intersection of the red and the green. Well, look at where the red is. The red is, first of all, it's everything outside together with everything in here. The green is everything outside together with everything in here. But you want the intersection of the two. So you want it to be both in the red and the green. So this stuff isn't in the green, so that doesn't count. This isn't in the red, so this doesn't count. So the stuff that's both in the red and the green is, again, just all the stuff on the outside. Same as that. See that? So these two sets are the same. Okay? Let's try the other one as well. In order to do it, I think easiest just to draw the diagram again. Okay, so there's your universal set. There's A. There's B. Okay. What does it say? Let's first do this one. This says to do what? It says you take the intersection of A and B. There's the intersection right there. Agreed? And you want the complement of that. So you want everything that's not right there. So that's going to be everything except the complement. I'm sorry, except the intersection. All that stuff. Everything except that. Okay, that's what this side is. Now let's take this other side. I got wiped away. Let's make sure that's good. Okay. First, what do I want? Let's do this one first. I want everything that's not in A. Everything that's not in A. Let's do it. Everything that's not in A. That's everything that's not in A. And then you want everything that's not in B. Everything that's not in B. So let's do that. Everything here. It's not in B. Okay, let's check ourselves out again. Okay, this set here is what? It's everything on the left-hand side. It's everything that's not in this little intersection. So that's the blue. That's the blue. Okay, now what do we have here? We have the union of two sets. So the union of two sets means all you have to do is be in one or the other one. See that? One or the other. You don't have to be in both, one or the other. As long as you're either blue or, as long as you're either red or green, you're good. So notice what's either red or green. All this stuff here, except for that, is either red or green. Agreed? Everything except this right here is either red or green. So again, we see that these two things are equal to each other, and that's the second of DeMorgans Law. So I think that's it. So that's a good review. That's really everything you need to know about set theory. Okay, just going to make sure that I'm still going here. Okay, very good. I'll just say one more thing. If you're interested, this is kind of extra stuff. But we talked about the fact that a set like, let's take the alphabet again. That was a finite set. The number of things in A was equal to 26. Okay, that's finite. If you can count them and put a number to it, then that's finite. If you can't put a number to it, like this set right here, then it's said to be infinite. Okay? And let's just take a moment to learn about some of the important infinite sets. Okay? In fact, I'll rewrite that one up on top. That's called the set of natural numbers, sometimes also called the counting numbers. And as I say, that's the set 1, 2, 3, 4, 5, and so on. Then the next important set is called the integers. It's called the integers. And the integers is what you get by taking the counting numbers and you take all the negatives of them and you also throw in 0. So maybe the easiest way to write them is to go something like this. Dot, 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 -3, -2, -1, 0, 1, 2, 3, dot, 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 like that. So there's the set of integers. And by the way, this is denoted with a N, like that. This is denoted with a Z. I think the reason is because this comes from a German word meaning number, as I'm told. Okay? Next one is called the rational numbers. Rational comes from the word ratio. I'll just say rationals. And there's no way to just very nicely list them off like this. I won't do it right now anyway. Instead, the way I'm going to write them is this. I'm going to say they're everything of the form P divided by Q, where P and Q, see this notation, are integers, So they're integers. And remember, there's one restriction, is that you can never divide by 0. We'll talk about that a little bit later in the course. But q cannot equal 0. Okay, so those are the rationals. Then finally, you've got the real numbers. And the reals, the easiest way to describe them is just all the points along the number line. Like so. Okay, they're all the points along the number line. And so there they are. And so can we get a Venn diagram that describes all of these together? Let's go ahead and do it. Let's start with the natural numbers. Here's your natural numbers right there. Okay, they live inside the integers, right? Because, oops, sorry, we don't use I for integers, we use Z. So a number like here would be 14 and 3 and 72. Those are all natural numbers. What would be things that are integers but aren't natural numbers? Negative 17. Negative 13, negative 5, 0 would be out there. Okay, those are all those. Then, those live in the, make this a little bit smaller. Those live in the rational numbers. And by the way, I forgot to tell you here, the rational numbers, you use Q for the rational numbers. You use fancy R for the reals and Q for the rationals. I'm not sure where this one comes from. But anyway, there's Q. And so what would be out here, which wouldn't be in here? 2/3, negative 5/7. You could write something as a decimal, 1375. Okay. So 13 over 2, for example. And this is a rational number because this you can write as 17 over 1. See that? Or over 1. So those are all rationals as well. And then finally, the rational numbers are part of the real numbers. Like so. And so the question is, what's out here? Are there some real numbers which are not rational numbers? And we will learn a little bit later in the course, this is one of my favorite proofs, that there are a lot of them. There are a lot of them. The square root of 2 is 1. The cube root of 17 is 1. Pi is 1. The number e, if you're familiar with e, is 1. Okay, if you make up a number that is a decimal that doesn't repeat or stop, like 1, 2, 1, 3, 1, 4, 1, 5, like that goes on forever. It never repeats. That would be these are all real numbers which are not rational. So these are called irrational. So these right here are called irrational numbers. I'll just put a little, and so those are there. So we'll say that irrationals. The irrationals are real numbers, but not rational. Or using the notation that we'd have R minus Q. Or since real numbers is our biggest one that we're talking about, we could just say Q complement, the complement of Q. If this is your universe right here, you can just say the complement of Q. Okay? So in a couple more sections, we're going to deal a whole lot more about this, but here's the cool thing, is that these are all infinite sets, and it turns out that in the same way in which you can have two different finite numbers, one bigger than the other, 12 is bigger than 3, also you have some infinite numbers which are bigger than others. It turns out that the number of irrational numbers that you have, even though it's harder to think of them, there are a lot more irrational numbers than there are rational numbers. In fact, if you were to just take a take a dart and throw it at the number line so that it just randomly hits a point along the number line, the chances of it hitting a rational number are 0. There are so many more irrationals than there are rationals that it will, with probability 1, it will certainly hit an irrational number. The chances of it hitting a rational number, even though you can count off billions of them, the chances of it hitting a rational number is 0. Really cool stuff. That's some kind of cool stuff in mathematics. So anyway, a lot of neat surprises in mathematics. That's why I enjoy it. So there's sets. That should do it.